So thank you for joining us today. Welcome to our seminar on 4D STEM precession electron diffraction. My name is Gareth. I'm one of the microscopy specialists at Quantum Detectors. We have 3 talks this afternoon. 2 of the talkers are with us in the room. One is downstairs on the microscope. After the 3 talks, we'll have a short question and answer session. Feel free to, after the session, speak to the people outside and discuss your research. We really want to encourage people to network in this session and again, share some ideas and techniques. So without further ado, I'm going to pass you to our first speaker, Matus, who will speak to you about MerlinEM.
Hi everyone, thank you Gary for the introduction. So yeah, I'm Matus from Quantum Detectors. I'm an application specialist for electron microscopy. In this talk, I would like to explain to you how MerlinEM hybrid pixel electron counting detector is useful for 4D STEM and diffraction. Quantum Detectors was founded in 2017 as a spin-out out of Diamond and Science and Technology Facility Council. So Diamond is a UK National Synchrotron Centre based just, and we are also based close by on Harwell campus south of Oxford. In 2014, the development of MerlinEM began at the University of Glasgow with Dr. Damien McGrother, who I was supporting with some technical stuff, but also working mainly on data processing of Merlin data. So our first commercial detector was installed in 2016 at the University of Antwerp within the electron microscopy for material science facility. We quickly started to engage with electron microscopy community and joined the STEAM project. This is a collaboration supporting transnational access to state-of-the-art microscopes in Europe, and it's supported by some of the largest institutes and universities like Ernst Ruska Center in Jülich and the University of Oxford. There have been over 50 installations of the MerlinEM detector worldwide and over 70 publications till now. So, and they covered many varying applications from imaging of virus particles to solar cell imaging or various diffraction techniques. So where do these applications come from? So this is actually image of me and Alex, who's downstairs running the microscope on the day we were installing the detector here. So this has been maybe three years. But what I want to illustrate with these pictures is that we closely engage with our users, and we help them to deliver and focus on their workflows to do basically spot-on research. And here it's the last picture of Professor Leo Molina Luna, who's kindly hosting this seminar in this group. So Quantum Detectors supplies 3 detectors for in electron microscopy, MerlinEM for STEM and diffraction mostly, MerlinEELS detector, and our new development for 100 kV imaging C100. In this talk, however, I'll focus on the MerlinEM detector on the left. So MerlinEM is a direct electron counting detector based on Medipix 3 chip. The detector is application-focused system, and we supply 4D STEM capabilities together with versatile and controllable readout. We have installed the system on microscopes from vendors, most of the vendors, and we have an interlock setup where we can basically install the camera opposite of a third-party camera. The key ability of the MerlinEM is that electrons are counted by advanced analog to digital technology. And this is done in each pixel. So before the data leaves the pixel is already digitized. And also that basically means that any subsequent process doesn't add noise to the readout of the detector. So this has quite good implications, because basically users can define a threshold. So this is the image on the bottom right, so basically if the electron deposits enough energy to overcome this threshold, the electron is counted. And so this threshold is set just above the background of, it can be selected further, but it's at the about the background electronic and thermal set of noises. And this will help with also, so as I said, readout noise as the digitization process, but also eliminating the dark counts from the detector, dark noise, and also blooming and other issues because we're detecting the electrons directly. So we can work with zero dead time. So MerlinEM can work with zero dead time to maximize efficiency of the imaging because there are two counters within the chip. The image on the left demonstrates the single electron counting ability. So basically, because of this versatile digital system, we can set the detector to acquire with 1-bit mode and achieve 18,000 frames a second imaging, which was utilized in tychography of those sensitive materials. And the two digital counters, excuse me, can be also combined together, and which is useful for high dynamic range imaging like diffraction. And in this case, this is the two counters were combined to get 24-bit depth imaging are done for, this is also just a polycrystalline grain sample. In this case, if we plot the profile, the contrast stems 4 orders of magnitude, and it's maximum at 10 million counts in the middle of the pattern. Okay, so I've demonstrated some basic capabilities of the detector. However, we need to see how these translate to real experimental applications. As I mentioned before, there are now more than 70 publications using MerlinEM detector, and this mainly utilized the exceptional dynamic range sensitivity and speed of fast frame rate of the detector. The main focus was at first with 4D STEM applications, like electromagnetic field imaging or tychography. But recently we had a lot more diffraction applications coming out of publications. So scan diffraction with or without precession, or tilt series reconstruction tilt series reconstructions are becoming quite more utilized. Also, additional topic is dynamic TEM imaging. So because of the fast frame rate, we can actually look at some specific experiments. So in this case, this is a skyrmion crystal where a couple of skyrmions are getting created and annihilated, and the detector can capture this sort of detail because of the fast frame rate. So let's step back a little bit and let's talk a little bit about the conventional STEM imaging. In this established STEM technique, the sample is rastered by fine probe, as we see in schematic on the left, and interacts with the sample, and we can detect the interaction after it passes the specimen. So this has been utilized for atomic weight information, phase contrast information, but also with additional instrumentation analytical information. Even though the conventional STEM detectors are fast, the distribution of scattered electrons, so here we basically collect few numbers. If this is a DPC detector, we get 4 or multiples, but we basically lost the distribution. It's average into a single or small number of intensities. Additionally, the established detectors convert the signal from electrons to light and photomultipliers so basically there's a lot of additional noise added through the indirect detection, and therefore it's not as easy to work with them with low dose imaging. However, if we utilize detector like MerlinEM, we can detect the full distribution of the electron beam. So this is a single example of a scan from set of perovskite samples. So there is different layers within the same specimen are just schematically shown here. But what it demonstrates is, is that there's a wealth of information which is not accessed. And so when we collect these data sets like this, we collect load them for every point of a 2D scan. Hence, we create 4-dimensional data sets and a 4D STEM technique name. So just to mention, we can see phase contrast information in the center of the seabed pattern. We have some higher order Laue zone rings across and Kikuchi bands through the image. So all of this would be summed in the annular detector. So because we've collected information about the STEM experiment, we can easily recreate this standard STEM data information after in post-processing. So I worked with Alex to get the data of this the sample titanium nitride and hafnium oxide interface, and I plotted the standard signals here, which are done by summing the particular angular ranges from the 4D STEM data. The important point I would like to make is that this analysis can be considered just a starting point. So once the 4D STEM data like this is collected, it can be analyzed by more advanced algorithms like tychography. We can look at symmetry breaking in this data. We can cross-correlate the beam positions and so on. So let's now have a look at what additional information we can get out of the 4D STEM detector. So in this slide, I selected example of how versatile a single data from 4D STEM can be. So on the left, we have these 4 images were generated from MerlinEM data from a single acquisition. So large angle annular dark field with phase reconstruction with tychography algorithm, in-plane electric field, and a total charge together. And this information was applied to map energetic land scale of this 2D semiconductor interface sample at atomic resolution. One of the first applications of 4D STEM was imaging of electromagnetic fields on nanometer scale. In this example, by Bruno Cesar da Silva from Institute NEOL in Grenoble, DPC imaging was used to image pin junction, which was biased by Holder. And basically, they were able to correlate dopants with the generated electric field directly. And this demonstrates one of the powerful applications of differential phase contrast imaging, and that's that it provides quantitative answers. As I mentioned before, Merlin is capable of imaging high-intensity beams together with low electron counts within the same frame, and therefore it's rather suitable for diffraction imaging. And so in this case, we image the sample with a parallel probe, so it's not convergent, it was close to parallel probe, and we can again collect 2D image of each probe position and hence get four-dimensional data. So I've plotted a couple of examples of how the dynamic range of the detector can be utilized. So in here we see the linear scale of the detector, where basically we see central beam at 300 kV. Also, we can see it, we don't need to use beam stopper. And also just plotted the wealth of information through the logarithmic scale. The particle experiment was utilized by Professor Paul Mitchell's group at the University of Cambridge, and they used MerlinEM to look at solar cell materials, which were halide perovskite samples, and they were able to analyze where the problems happen and improve them. These particle materials are very beam sensitive as well, so other techniques like X-ray imaging also lack the resolution to find the essential information about these samples. We expect that scanned diffraction techniques can be applied to many challenging systems which weren't as easy to analyze before. As a last example, I would like to show you microelectron diffraction acquisition. So basically, we can continuously rotate the sample or do it in steps. So in this case, data has been collected from propane propylene sample, where the two compounds were suspended in this covalent organic framework 3D structure. So once we collect this 3D data set, we can reconstruct the information in the diffraction space, and from there match the structure of the sample with different libraries. So in this case, I would like to show you a short video of how MerlinEM data can be opened quickly with LibreTem. So basically, I can I see the screen moving. So basically, we can once we have this GUI started, we can open the data, select some parameters of the data set. In this case, it was a 256 by 256 pixel scan, and basically now we are ready to analyze it. And then once we click at different analysis, we have standard STEM signals available as a ring or disk data, but also other more advanced algorithms. And so I selected the ring data here, and we can see the view of the sample. So it's like slowly averaging on the background. And now I select the particular angular range I want to generate the annular dark field, or in this case, high angle annular dark field image. So basically, once I tune the geometry in the video, I can I'll click on apply, and this analyzes the data. And what I can show you that this doesn't take too long. It was also done on on this laptop, so it's a fairly fast process for summing the data and getting the sort of quick information about the sample, and being able to judge whether the data was right. You can also use this to collect analysis. So we can generate, so the image on the right can be downloaded. So it's a web interface, so it looks like I'm taking it off internet, but basically I can just click on a specific link, and that's my 32-bit TIFF file with the information I generated from the given data. I think you can also select the left side, so you have the reference where the radii was taken from. So here I just demonstrate the same thing, but as a bright field detector. So I place my virtual disk in the center of the beam, and I can generate phase contrast information on the right side. So we'll wait a few seconds. I think LibreTem also times this, so it should be around 16 seconds for these data sets on that particular laptop. Right, so one thing to mention as well, that the LibreTem comes with additional interfaces. So it's a full Python framework to work with for distant data. So this is just a small part of what they actually do. So they work on tychography. They can collect live tychography with our detector as well. So there is more to this applications than I just showed you. So with this, I would like to summarize my part of the talk. If I can get out of the video. Yeah, so I want to mention that MerlinEM is a versatile and integrable detector. It's compatible with most of the microscopes manufacturers. We can synchronize with different hardware and software solutions through TTL signals, LVDS signals, but also we use TCP/IP control to to work with the detector remotely. So we have a nice GUI who you will hopefully see downstairs, or some of you who are interested. But we can run the detector remotely, and we supply examples from Python and digital micrograph of how to actually do this. And this is on the right. You see a selection of people who are who integrated, or institutions and companies who integrated and work with the data sets and data streams directly from the detector. Thank you for your attention.
Just bear with us for a second while we swap over some of the tech. Thank you very much for the talk, Matusz. We'll now have a talk from Thanas Galanis from NanoMEGAS on the technique of precession electron diffraction.
Good afternoon, everyone. So I have seen many of you also to our lunch seminar earlier today. So I will repeat some of the presentation, or part of the presentation also on this seminar. Okay. So NanoMEGAS is a company based in Brussels that we are expertised in precession electron diffraction. So all the applications that we have are based in precession electron diffraction and are hardware based. So those are our applications. The first one is just a brief introduction on this. The first one has to do with electron crystallography. So it is a kind of 3D electron diffraction tomography to collect data and determine a crystal structure. The second application that we have is phase mapping and orientation mapping. That it is a technique like EBSD method in scanning microscope, but we have all the benefits of the transmission microscope, and you can do in these maps in much higher spatial resolution. The strain mapping technique is again a kind of generation of this kind of maps, has mostly been developed for semiconductor materials. And the last application has to do with characterization of amorphous materials by a technique that is coming from X-ray world and is named per distribution function for those that they are not familiar with. So all these applications are hardware based, and a software is dedicated for any of these applications that the user wants to apply. Okay, again, I have shown this earlier today, but for those that are not familiar with precession, instead of having a parallel beam passing through our sample here and obtain a diffraction pattern, what precession does is to tilt the beam before and after the sample. And the effect of this actually is a movement of the eval sphere. And at the same time, we have quite fast rotation of this tilted beam around the arbitrary axis. And what you obtain at the end is all these diffraction patterns together. Okay. So what is the effect of this precession? The effect is that we have higher order reflections. So we improve the quality actually of our diffraction patterns. We have higher resolution, and also we have reduced of the dynamical effect that we always have in transmission microscope because of the interaction between the beam and the sample, the strong interaction. So here is some diffraction patterns of a mineral without precession and with some angles of precession from 0.5 up to 3 degrees. And you can see that even with 0.5 degrees of precession, we have far higher order reflections, so we can see more far reflections from the center. So we increase the resolution, and then as we go up on precession angle, you see that we have also some change of the intensity of the reflections. And the reason is that we reduce the dynamical effect when precession is applied. So we go more close to kinematical intensities, or more close to intestines that you obtain also with X-ray. We'll never have poor kinematical intestines, but we are at least approaching more kinematical intestines. So, okay, now, again, I think we showed it yesterday. Okay. In this seminar, we will focus mostly in these two techniques. So phase and orientation mapping and strain mapping. And these techniques can be called as 4D STEM, or another name that is, you can find it in literature, is 4D scanning precession electron diffraction. The conditions are not the same as STEM conditions, so we prefer to have a different name compared to STEM. So 4D scanning precession or probe electron diffraction, as we heard earlier today. So the data are acquired by this 4D SPED. And how it works, we have the beam, a pseudo-parallel beam, that goes through the sample, and then this is the diffraction pattern without precession. When you apply precession, the quality of the diffraction pattern is improved. You can see this diffraction pattern is the same with the previous one, but with precession. And as we have this precession, we start scanning the sample. So we scan the sample, and for every point, we collect one diffraction pattern. So you can collect thousands of diffraction patterns, and then all these diffraction patterns can be used depending on the application that you want to use, okay? So because today we'll speak about a combination of our technique with direct electron cameras and Merlin camera, I will focus a little bit on this. So standard package is using a CCD external camera that collects data from the phosphorus screen. And this is a method that has been applied the last 12 years or more, and quite successfully. And even if the camera is not the best quality, we have sufficient data to obtain quite good quality of orientation and phase maps. Yeah. However, lately we have developed our method to be compatible with more high-end cameras and direct electron detectors. This is one of the cameras is a Merlin camera for quantum detector. This is the platform that we are using for the data acquisition of 4D SPED. And it is compatible with Merlin detector, and you can see that the quality of the diffraction patterns is improved dramatically. Yeah, this is some experiments that has been done in University of Glasgow, and we compare here the results that can be obtained by either by the Stingray or the direct electron detector. You can see even from the virtual bright field image that this image is more sharp, so we have better contrast and it is better quality. And of course, also in the phase mapping and the orientation mapping, we can see much more details when this direct detector is used. Okay, back to our NanoMEGAS applications, what you obtain with phase and orientation mapping. So except of the orientation map, a typical orientation map, this is a multi-grain sample, and the virtual dark field image, you can have some more tools like grain boundaries map, some texture analysis to understand if you have a preferable orientation of your grains, grain size distribution, and another kind of a map that is called correlation coefficient map, that if you see some details here, it gives somehow details of 3D overlapping or projection of your grains on a 2D map. Okay, this is what you obtain. The important thing is here that using a field emission gun transmission microscope, you can go down to a spatial resolution of 1 to 3 nanometers. The method is quite fast and straightforward, so it's easy to apply also for in situ experiments. You can have, as I said, orientation map or a phase map. And this is another tool that it is named as an interactive virtual dark field that you can have for every pixel of your diffraction pattern series. For every pixel, is it working? Yeah. You can have the virtual dark field image offline, just scanning your diffraction pattern, and you can see many local details of your sample. Okay, strain mapping uses again the 4D SPED method for data acquisition. The previous application that I told you, the orientation and phase mapping is using a kind of template matching. In this case, for the strain analysis, we need to compare all the series of diffraction patterns that have been collected with a diffraction pattern that is coming from a known strain area. So in this case, we need to be in to have a single crystal and all our data to be collected from a single crystal that would be zone oriented, and then compare the series of diffraction pattern with a reference pattern. Yeah, what we obtain at the end is strain maps like this in X and Y direction. Whatever you see, this red color means tensile strain and blue color means compressive strain. You can, of course, have some strain profiles. And the important thing here is that we can go to spatial resolution down to 1 to 5 nanometers. And we can have strain sensitivity that can go down to 0.02% of strain detection. Okay, more details about all these applications you can see in our website, as the time is limited. NanoMEGAS is part of STEAM3 consortium. So if any of you wants to make some sophisticated experiments like this, there are labs in STEAM3. You can apply. You can apply for a few days of experiments and go there for free or almost free. Okay, that's it from my side. So thank you very much.
Hello from the microscope. So basically, you entered this beautiful material science building here at the campus in Darmstadt a few minutes ago, and you are currently located in the very back of the building. And we are just sitting 1 floor down from you at the microscope. And with me today here is also Despina, Oscar, also in the back, 2 PhD students of the group of advanced electron microscopy. I think later on Thanos will also be here. But yeah, I have just a few slides prepared, and obviously the live demo, which I will show in a minute. I'll just go through the slides to explain what sample we are looking at and what the setup actually looks like here in Darmstadt. So here on the left, you can see the Merlin detector, the quantum detector's Merlin detector, before being mounted to our system. And actually here on the right, you can see the image of where the Merlin detector is mounted opposite to one of the cameras that was pre-existing on our system. And there's actually an interlock that actually prevents both cameras from being inserted at the same time. So there's no danger of crashing these into each other. And basically, every detector waits for the other one to be retracted. In this setup, basically, the Merlin detector sits below the bright field detector on that camera box and just above the yield spectrometer that you can see here on the bottom. But later on, I hope we can do that. We will also remove the cover, so when you come downstairs to the microscope, ideally you will be able to have a look at this So for the different modes that Matusz and Thanos now explained in great detail, this is like an overview schematic of how all the computers work together in conjunction. Due to time limitations, we only have the option to basically show one setup today, and that is basically the one that you see down here. What we normally also can do here is obviously what Matusz told you in the beginning, the convergent beam setup. So let's say the normal STEM setup with the convergent electron beam, where the beam scanning is controlled by the JEOL PC, and then a trigger is sent to the quantum detectors hardware to trigger the acquisition of a frame and to capture a 40-step data set. What we will do today and what we will focus on now is the setup in blue down here, where basically the centerpiece is the NanoMEGAS PC where the topspin software is running. And that PC is basically controlling all the camera settings of the quantum detectors hardware system. And the hardware scan unit that controls the beam position on the sample, as well as the precession mode of the electron beam. This is also triggering the quantum detectors setup, so the system knows when to take a frame. So also what I want to tell you, I will be switching shortly to the quantum detectors TC to just show you that the software is running in the background and images are transferred over the network to the topspin TC, which I will be showing most of the time. And this is also where you can see the screen from right now. So yeah, obviously about precession electron diffraction, I don't have to tell you a lot more now after Thanos' talk. So just keep in mind those electron diffraction patterns that you can see here on the right. One is acquired without precession, one is acquired with precession on the actual data, on the actual sample that we will be looking at now. And obviously, as a Materials Science Institute, I will also give you a very quick introduction into the material system that we are looking at. We're just not using a demo sample, but actually a sample where we acquired data very recently. And I think 3 weeks or 4 weeks ago, I think there was a paper released. So if you have also material scientific questions, I will point you to Fernando on the next slide. But yeah, the sample that we will be looking at today is a manganese aluminum alloy, and it's a permanent magnetic material, so of the L10 type. And to have the magnetic properties, you actually need the material to be in this tau phase that you can see here in the phase diagram in the center. So what you start off with in the beginning, you start from the melt and you quench the melt in the correct composition to the epsilon phase. And that epsilon phase just has a random distribution of the manganese and aluminum atoms in the crystal structure. And then by a very, very careful annealing step, you will actually go from the epsilon phase to the tau phase to gain the magnetic properties. And this careful annealing step can be done in different ways. But Fernando Macari, who is also a researcher here at the TU Darmstadt, and he should be present, I think, in the room upstairs. I'm not sure if he was able to make it. Basically, he did, he basically cooled or quenched the melt in this process here to the epsilon phase. And then after that, he used current assisted annealing to get the material system from the epsilon to the tau phase. So in this current assisted annealing step, it's possible to control the annealing procedure very carefully. And from one of these samples that is in his work, focused ion beam prepared sample was cut. And actually one of these samples is in the microscope right now. So yeah, as I said, if you have material scientific questions, you can hopefully address these to Fernando. But I will basically switch to the sample right now. So these are just overview images. This is what it should look like in the microscope. I'll just end the presentation here, and I will switch to the quantum detector software. And what you can see here, or it's not very visible right now, but yeah, there's this small feature here in the center. This is the sample that we will be looking at. And just let me switch now to topspin, where we have the same view. So as you saw, topspin is right now just gathering the images that the quantum detectors is capturing. This is done over the network connection. So you have to trust me a little here because the contrast is not very high, but here in the center, there's the region of interest that we are interested in. And I will actually go ahead and just converge the beam to a spot. Because as Thanos explained earlier, we want to have a probe on the sample plane. Just a little. We want to have a probe on the sample. I actually forgot to take an overview image, which is not that important. Just go to the scan range here. And what we see right now is this is just a preview of the area that the beam will be rastering in a second. So basically I can acquire an image before and now have an overlay of where the probe will be rastering the sample. So with this, I'm actually quite happy. I will quickly introduce you into the software interface of topspin as well here. So basically, as the software is set up right now, it's set up as a precession electron diffraction experiment. It's just the same experiment that we did for the recent publication, and we will acquire a data set that is actually resembling the data set from the publication as well. And here on the top, you see the different steps that you do in order to gain one of these data sets. So we will go step by step through this until we can acquire a data set at the last step here. And on the left-hand side, you have all the options for controlling the different parameters. But yeah, what I will show you now is basically just the automated alignment functionalities that are within, like implemented within topspin. And this is actually one of the most amazing features I still find, because topspin right now at this moment is like trying out different alignment parameters. And it's doing that much faster than a human can do. There's an algorithm that basically just checks at the same time if the alignment is nice and well. So we want to have a probe that's not moving on the sample, which is the case right now. So once I'm happy with it, or once topspin decides that it's fine, it will stop the alignment process. And we are good to go to the next step. I will switch the microscope to diffraction mode. So you can see, I hope you can see that on the projector upstairs, but we can already see a diffraction pattern. What I will turn on now is actually the rastering of the beam on the sample. And here I just am using diffraction focus to align the first projection length strength to the correct height to basically capture the diffraction pattern. So there's minimum D-scan. And this is the case right now, so the pattern is just moving slightly. I can move that a little more, but that's perfect. And in the next step, we will record a low resolution overview of the sample. We can basically select the number of pixels. We can already have a look at the diffraction pattern and move it across the sample. And basically, I will just start this overview scan now to use the time wisely. What is being displayed here on the left is now the intensity that is integrated within that blue aperture that I set up here on the right-hand side, meaning that right now a virtual bright field image is being generated. So whatever we see here is just the integrated intensity, and it's currently being done live. So the beam is right now rastering across the sample, and lo and behold, we do see the region of interest that we are interested actually perfectly in this frame. Perfect, so we will just let this finish. And I can proceed to the next step, which is another alignment step. In this case, it's the precession D-scan. So as Thanos showed, there's these two sets of deflectors. And right now I can do the optimization for the deflector set that sits below the sample plane. And actually this, it looks quite all right already. So maybe I'm just lacking a little bit of threshold here. Okay, so maybe, yeah, I do not have enough intensity. Maybe there is a little bit of sample, of carbon contamination on the sample right now, and that's why it's not doing that properly. But the alignment is fine so far. Sorry for that. If you come downstairs later, I promise you we can do this step one more time. And yeah, now I will basically do one thing. I will again check a single diffraction pattern here. Check if the aperture is set correctly. In this case, again, right field aperture. And right now, topspin is scanning the electron beam across this kind of feature. Again, this is current contamination because we had the beam sitting there for a short amount of time. This is perfect for this alignment step. So we see the decrease in bright field intensity when the beam is rastering across that, which is like our first step here. And now we will do the same thing with precession enabled. So right now, topspin is scanning the beam across that line, but at the same time, the precession motion of the electron beam is also enabled. And basically, this is just a step for us to check if the alignment is all nice and well, because there should be no shift and nothing here, but this looks perfect. So we can actually proceed to the acquisition of the data set, which is on this series tab. We could also set up drift correction, but because this is a sample that has rather large features, and the sample was in the microscope already until yesterday, we don't see any drift, and I don't need to set up that right now, but it would be available if you would be interested in higher resolution data sets. So I can basically set up the step size or the pixel size here on the left. And with this blue rectangle, I can just choose the area of interest that I want to record data on. And I will actually go ahead and do that right now. So it's just appearing here. Yeah, so that looks fine. And once I click on the acquire button, topspin in the background will just prepare space on the hard drive because, as you heard, we will be recording quite large data sets. So this is one of the obviously features of this method. And as you can see right now in the animation here, the yellow dot is the current beam position of the electron beam. In the view in the panel here on the right, you can see the actual diffraction pattern that is being recorded right now. And on the bottom right here, and I can also magnify this so you can see it a little better. That's again the bright field image that's generated live, but at the same time, for every beam position, the 2D diffraction pattern is saved correctly. So with that, because obviously this takes some time for the analysis part of the live demo, I would switch to this exact data set that we recorded a little earlier, just to save some time. So I will leave topspin running in the background, and I will switch to A*STAR, which is the software that we will use for analyzing this data set. And just to orient yourself again here in the center, what you can see is the inclusion or that secondary phase that is formed in the sample. And basically, as I drag the cursor over this data set, here on the right, there's already a diffraction pattern. It's just inverted in contrast being shown. And at the same time, this overlay in red or green is already a live matched template. So Thanos explained this, that we basically go from the crystal structures that we expect for this sample. We can load these crystal structures as templates down here in the template manager. And basically, software is doing the fitting of these templates live as I drag across here. What we can see is that basically we have a very big epsilon phase grain here on the right, on the left, and we have another big epsilon phase grain here on the right. And between these grains, and this is actually quite amazing to see on the material scientific side of things, right at this grain boundary in the current annealing step, a tau phase grain was formed. And there's a little more features inside here. And I would be able to now just also run the indexing. But again, for the demo, we also have the analyzed data here, so it's a little quicker. And maybe it's hard to see in the software interface. So I will actually go back to one slide that shows this data set quite well. Let's just maximize this. And here you can actually see the difference between using precession electron diffraction and just the same data set acquired with the precession turned off. So on the top row, you can see the data set with precession turned off, and immediately see what you can see here in this index map, which is kind of a measure of how easy it was for the template matching routine to attribute a template to the recorded diffraction pattern. You see a lot of noise. So the software was not really sure on which template to use. Or maybe it could not decide between different orientations of the crystal of what to match. And once we turn on precession, and this is with a precession angle of 0.5 degrees, the noise is basically gone, because the quality of the diffraction pattern improved so much that the software has a much easier time on deciding on which phase and which orientation to match to the experimental diffraction. And you can see the same thing in these phase maps. And as I explained earlier, we have this tau phase grain here in red inside this matrix of the epsilon grains. And this is displayed quite nicely. And as you can see, with precession turned on, the interface is also much sharper than on the grain that you see here on top with no precession turned on. And as a secondary information that we can extract from this data set, I also drew some line profiles across that even smaller inclusion in the tau phase grain. And this is something I did not explain yet, but it's a solid state phase transformation, the transformation between the epsilon and tau phase. And during this basically ordering step and share step in the phase transformation, there's a high probability of twins being formed in the tau phase. And for these twins, theory predicts that there's a misorientation angle of 76 degrees between the two twins in the tau phase. And if we draw a line profile around that dotted line that you can see here, we actually do see a misorientation of exactly 76 degrees, which is also quite important to see, because this is, as I said, current annealed sample right at the verge of being transformed completely from the epsilon to the tau phase. And it's like we are capturing that moment in time. A focus ion being prepared lamella is inside, and we can basically see that snapshot of the phase transformation. It was quite important to see. And with that, I will actually conclude the live demo. I'm looking forward to meet you also downstairs here at the microscope. You can have a look at the system, and we can maybe show some of the steps that might need more time explaining. But so far, thank you for your attention.